Review for Nelly and the rest of y'all mortals. And a bunch of those. Cross off X on number 3 that I just gave you. Oh, thank you.
Mac, we're bringing numbers back into this?
Yep. Just briefly before the quiz.
Oh, hell yeah, I got this.
Okay. Oh, McKenna needs one. Cross off X on number 3. Sorry. When I was making it in my head, I was always solving the wheel, and I changed it over down. No, we're not doing that. We're not doing the Joker thing. Okay.
Max, literally just a rare sight of a new pencil. That was the only joke. You turned it into a dipshit. What? I did. I got it the first 2 times.
Cross out X on number 3. Oh. Yeah. You're sitting there, right? Yeah, that's what it is.
Yeah, but we didn't even finish it.
We need a page. Okay, good.
He was coming for wrestling and he tried to shut his mouth.
White line.
Yeah, we had actually. I didn't delete it because I don't want to pop it. Because I don't work down here. I'm sorry.
And his was broadly, and I
Oh, wonderful. Is it your birthday?
No.
No, I knew when your birthday was. You were talking about it forever.
Yeah. Kind of. When's my birthday?
It's like at where mine lies.
My feet hurt.
I would ask when's my birthday back, but not my parents remember that.
February 10th.
Big yikes.
I did though. I got like.
I stare at your health poster every single day. Like, you wrote it in like the 2005 10 too, and I was like, why is it like that? Is his birthday December 2nd? Yeah.
It's a shitty.
Yeah.
Yes, it is.
Oh, can I get home today?
Yes, yes. Hey, I'm here super late tonight, guys, so if you need help, come in and get it.
Oh, guess who's coming?
All right. Nerds. All right. Yeah. All right, we're not looking at that packet or the piece of paper that I gave you. We're not looking at that yet. We're going to do it at the end if we have time. Okay? If not, it's homework, but it'll totally be easy. Okay? So, reviewing what we did yesterday for Nelly and for the rest of you mortals. So, that's right. So, we know I need your A game today. A game. Dolschlager? We had a conversation. You remember it? Wonderful. So, guys, if we have this, right? We learned yesterday that by perpendicular bisector theorem, which we proved, Nelly, we did actually prove this to be true, that if you have a perpendicular bisector, so if we have this, right? This is the perpendicular bisector of this segment, right? Then the distance from this point to this point will be equidistant to the endpoints. And it's true for any point on here, actually. So this will be true. If I had another point here, I could connect it, and it would also be equidistant, okay? So we know this. That's by perpendicular bisector theorem. Okay. We also know the converse is true. We proved that yesterday. That if you have this, right? We have a point that's equidistant from the endpoints of this segment. Then that means that if I were to draw the perpendicular bisector in for this segment, this point would be on it. Okay? And that's the converse. So that's perpendicular bisector theorem, converse. Today we're going to once again review, so you can just watch, that perpendicular bisectors of a triangle are always concurrent. Okay? In order to do that, we're going to have to draw some perpendicular bisectors, and I just want to clarify what you're allowed to be like, let there be this and let there be that, right? What you're allowed to do and what you're not allowed to do. You are allowed for any triangle to say, let there be a midpoint, right? Because every length that I give you is going to have a middle, right? You can always cut something in half, right? So you can say, let that be the midpoint. And we know we're always allowed to connect dots, right? So I'm also allowed to say, let there be a line. In other words, let there be a median, right? So vertex to midpoint, you can say, let there be that, right? That's totally rad. You can also, for any triangle, say, let there be an orthogonal, otherwise known as vertex to 90, right? Even if it's a really weird triangle, like an obtuse triangle, there will be an orthogonal here. You'll just have to extend the side out, right? Now, typically when we do proofs with orthogonals, we do it with these kind of triangles, acute, because the proof will be the same, but just way less messy, right? Okay. So vertex 90, totally fine. There's always a way to draw a 90-degree angle from a point. Always. You're also allowed to, for any triangle, say that this is the midpoint, right? We talked about that earlier. And then say, let there be a 90-degree line perpendicular to that. That's totally fine, right? If I give you a line, can you draw a line that's perpendicular to it? Sure, right? Here's a line. What's perpendicular? Here. Right? Makes an X. So midpoint to 90. From the midpoint up to 90, right? Up at 90. What you cannot say for any triangle is all three at once. So we said vertex and midpoint together? Sure, right? Vertex and 90 together? Sure. Midpoint and 90 together? Sure. What you can't do is vertex, midpoint, and 90 at the same time for any triangle. Watch when I try to do that. Midpoint, right? 90 straight up. Does it necessarily go to the vertex? No. I don't know that that's 90. I can't just say let there be that, right? So it's okay to say let there be a perpendicular bisector. It's okay to say let there be an orthogonal. It's okay to say let there be a median. But you can't say I want a perpendicular bisector that also goes through a vertex. Can't guarantee that, right? Only an equilateral triangle or an isosceles triangle will have that happen. And the reason for that is this, right? If it's isosceles, we get that, right? Guaranteed. The perpendicular bisector will go through the vertex. If it's equilateral, even more so, right? Cool. So what we're going to do for this proof that the perpendicular bisectors of a triangle are concurrent is we're going to construct perpendicular bisectors. Remember, that's these guys. Don't necessarily go through the vertex, right? So let's do that. I'm going to say let this be the midpoint of this side, right? That's the bisect part of perpendicular bisector. I'll call it point D. And then I'm going to take out my ruler. I'm going to draw a perpendicular to that, to BC. So this is the perpendicular bisector of BC. Okay? We can do that. That's fine. Every side's going to have a midpoint. Why not call D that? There's always a way to draw a 90-degree line to another line. Okay. I'm going to do that for this side too. So I'll call this, let's call this E so it actually goes somewhere. I'm going to call this point F. Like your report card.
Huh. Thanks, Mac.
And then we're going to draw a line from here to here at 90. We're going to call it FG. Like the homies. All right. Now, do we agree that these lines are going to intersect somewhere? They have to. If they didn't, they'd be parallel. And imagine a triangle that you drew perpendicular lines from that would be parallel. It'd have to be like this, and then they'd be perpendicular and never intersect, right? It wouldn't be a triangle. You'd have to have the two sides of the triangle be like this for them to be parallel when you drew perpendicular to it. So we're going to assume they're going to intersect at some point, right? These aren't going to be parallel no matter what kind of triangle you draw. So let that point be K. Why not? Okay. And I'm going to prove that if I were to draw the other perpendicular bisector, it would also have to go through K, right? Two lines intersecting, no big deal. all three intersecting, being concurrent, we can't assume that, right? We have to prove that. So I'm going to prove that if I did draw the other perpendicular bisector of this guy, it would go through K. So what do I write to create all that? Well, I say let there be, or just let FKG be the perpendicular bisector of what? What side is FKG the perpendicular bisector of? What side of the triangle? AC. I'm going to call it AFC. That way we know it intersects there. Okay. Remember, if they share a letter, whoops. If they share a letter, that means they must intersect there, right? And I'm going to do the same thing here. I'm going to call it DKE. Be the perpendicular bisector of what side? I'll zoom in. What side is DKE the perpendicular bisector of? DC, or BDC, yep. Who made the beginning of the alphabet rhyme? Awful. Should use like Bravo, Delta, what's C? Charlie, right?
I mean, D can be very, very many things.
All right, cool. And the K here tells us that they must intersect at K, right? Because they both have K. So cool, we created those. No big deal. Now, I'm going to prove that K would also be on the perpendicular bisector here. Here's how I'm going to do it. By perpendicular bisector theorem, remember that's this guy? It says if, or the converse, let me say that. If it's on the perpendicular bisector, then that point will be equidistant to the endpoints, right? Isn't K on the perpendicular bisector of BC? It is, which means it's equidistant to B and C. So I'm going to draw that. These must be the same length. In other words, they're congruent. Cool. Has to be. Has to be.
Wait, can I see that again?
We good? If you want a protractor, there are protractors around here. Nice.
Did you see my phone?
Yeah.
Thank you.
Girl was born ugly. All right. So, what? Just the pictures on her phone makes it look like that. Hi. So, isn't K also? Isn't it also on this perpendicular bisector? It is, right? So it should be equidistant to C and A. I drew this really poorly, so it's not going to look equidistant, but trust me, it is. Okay. So K is equidistant to C, and it's equidistant to A. And this shouldn't surprise anybody, because when the perpendicular bisectors intersect, that point K, what center is that? What triangle center is that? Perpendicular bisectors go with what? Katie?
In center.
Close.
Oh, yeah.
Circumcenter, right? And the circumcenter is a circle that goes around the triangle. So what kind of lines are these, Katie? These blue lines? If I were to draw on my circle, the blue lines must be? Anybody? They go from the center of the circle to the outside of the circle. Yeah? Well, they're congruent, but what do we call them? Radii.
Oh, cool.
Radii, right? They're radii of the circle that would go around that. That's the center of the circle that would go around it, right? And those are the radii. That's why they're all congruent. Okay? If that helps, great. If it doesn't, don't worry about it. Okay? So, now I'm going to use the converse. If a point's equidistant from two others, then it must be on their perpendicular bisector. Now, you with me on that? All right, okay. Let's check it out. Isn't K equidistant from A and B? It is, isn't it? Right? It's equidistant from A and B. So therefore, it must be on their perpendicular bisector. Right? If it's equidistant from 2 points, then it's on their perpendicular bisector. It's equidistant from A and B, so it's on their perpendicular bisector. So let me write down what I've done. I said, by perpendicular bisector theorem, I learned that BK, AK, and CK are all congruent. So those lines I drew in, right? How did I know they were congruent? Because K is on this guy's perpendicular bisector, so it's equidistant to his endpoints. It's on this perpendicular bisector, so it's equidistant to the endpoints. And then I use the converse. BK, yep. By that converse, if K is equidistant to A and B, then it must be on this guy's perpendicular bisector. So by this, K is on the perpendicular bisector of AB. Right? AB's perpendicular bisector. Well, if it's on AB's perpendicular bisector, and it's on BC's perpendicular bisector, and it's on AC's perpendicular bisector, then the perpendicular bisectors are all concurrent, because they all have K in it. This guy would have K too, right? So they're all perpendicular, or they're all concurrent at K. Therefore, yep, the perpendicular bisectors of triangle ABC are concurrent. They all intersect at K, right? The first two did randomly, right? And I proved the third one had to go through it as well. This is not a technical proof where it requires lots of different theorems and you got to see lots of, right? It's not. You've got to see it though. 90% of geometry is seeing it. It's like an optical illusion. Once you see it, it's like, oh, of course I see the boat, right? But if you don't, it seems impossible. Which is why watching this in real time, instead of just tuning in every 5 seconds or looking up when I'm done, is a way better way of learning. So hopefully you're taking advantage of that. If not, you can watch it live or recorded live on YouTube. Or come see me. I'm going to be here super late tonight. But watching it as it unfolds makes a lot more sense than just if I went, hey, look, this is true. Write that down. Do that on a quiz, right? First we draw our perpendiculars, perpendicular bisectors, right? 2 of them. And then we prove these lengths are all the same. And then we use the converse to say that K must be on it. One of the shorter proofs we've done. But it takes some knowledge. Yeah.
Okay, so I understand like the radii part, like how the
Up to there.
they're all equal because of the because of the theorem. Because
Yep. Mm-hmm.
yeah, okay. But like the bottom part.
This.
Yeah.
So K was equidistant to A and B, right? We proved that. If a point is equidistant to 2 others, then it must be on their perpendicular bisector. Okay? So if it's equidistant to A and B, then it must be on the perpendicular bisector of AB. Better?
Yeah.
Okay. Words are hard, like perpendicular bisector. It's a mouthful, right? Okay. But once you get over that, this line thing, right, it's going to be on. Yeah.
So, like, are all those lines, like, needed to prove that triangle ABC always have
So the first 2 were concurrent because I just had them intersect at a random point, right? The third one you don't have to draw in. I was just showing you that it would be. Did that answer your question? Okay, all right. All right, gentlemen in the back, I swear to God I'll move one of you up front and center. Let's look at page 13. And before we do that, let me remind you of what we're trying to accomplish here. Okay? There's a little bit of a lemma. We learned a while ago from a proof where I gave you this. Okay? What we did is we made a triangle and we made midpoints and we connected them all up. Those are called mid-segments. It's another special segment of the triangle, but we don't worry about them so much. The triangle that you make when you do that to any other triangle, if you have a triangle and you connect it to midpoints, it's called a medial triangle. Okay? Every triangle has a medial triangle. Because any triangle I draw will have midpoints. And we can always connect the dots, right? That's the medial triangle. Okay? Now, medial triangles have special properties, and we proved this a couple weeks ago. We proved that this triangle here is similar to the big triangle, right? Which said that these angles were the same, right? And these were shared, right? Because they're similar. Which means that these sides are parallel. right? And so on and so forth. This side will be parallel to this side. And this side, we already said was parallel to this side. And that this side will be parallel to this side. And not only that, but that side's always half of this guy. 3 marks, right? Always half. Same thing here and here and here and here. So whenever you have a medial triangle, and all triangles have them, right? You get congruent segments, right? This is double of that. That's double of this. That's double of this. And you get parallel lines. Super useful, right? Parallel lines get us a lot of angles. Congruent sides, well, they're congruent sides. Super useful, right? What we're going to do today is do the reverse of that. We're going to be given a triangle. Okay? And what we're going to do is we're going to say that's the medial triangle of a bigger triangle. Here's how we're going to do it. We're going to say, I'm going to make a line parallel to that. I'm going to place it right here. Okay? I'm going to make a line parallel to this. I'm going to place it right here. What's the last color I should use?
Yellow.
Yellow. Twinsies. And it creates a bigger triangle, right? The same color lines are parallel. We cool with that? I'll call that where they intersect DEF. So we create big triangle DEF, and the original triangle, the OG triangle, that's a medial triangle, right? So by medial triangle theorem, converse, because we went backwards, right? We started with the medial and made this guy. We know that this and this are congruent, right? Because it's double in half. This and this are congruent because double in half, right? And this are congruent by double in half. You with me? Okay. And again, parallel, right? We cool with that? Right. So, doesn't that mean that A, B, and C are the midpoints of the big triangle? They are, aren't they? Are we cool with that so far? I'm going to stop, let that breathe. Right. I just did this in reverse. Instead of drawing a big triangle and finding the small one, I did the small and made the big. Is it? All right. So, if I were to draw a line from here, let's say at 90, right? Call this 90. Hold on, relax. Don't see the triangles. Focus on the line. I'm going to call that, isn't that a perpendicular bisector? Totally valid. I just made the perpendicular bisector to the big triangle. Totally fine. That's the midpoint. Draw 90. Right, we're good. Here's the thing. Aren't these parallel? It's a transversal! Inside the parallels, opposite side of the transversal. By alternate interior angles theorem, that's 90. Now pause. If I were, let's use bright green. If I were to highlight this part of my perpendicular bisector, what kind of line is that in the small triangle? It's an orthogonal. It's not a perpendicular bisector because it doesn't cut the side in half. We don't know that, right? But it's an orthogonal, right? Vertex to 90. So now I'm talking about the orthogonals of the middle triangle, right? And that's what I'm going to prove today, that they're concurrent. So the perpendicular bisectors of the big triangle give us the orthogonals of the small triangle. I'm going to do that again. Do it again. Right. So I'm going to draw a 90 degree from here. Right. Perpendicular bisector, totally rad, no big deal. Boop, bloop, 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 bloop. Right. These are parallel. That's 90, so that's 90 by alternate interior, right? And if I highlight just this portion of it, vertex to 90, what is it? Orthogonal. Now we shouldn't be surprised that our perpendicular bisectors intersect at one point. We just proved that, right? That they always do. Turns out the perpendicular bisectors of the big triangle are the orthogonals of the small triangle. Last one, I'm going to have to cheat a little bit because I obviously didn't make these really parallel. If I draw a perpendicular bisector from here, perpendicular, yep, that's perpendicular. Trust me, that's a 90-degree angle. Never seen a better 90. Right? Parallel, alternate interior. So this is an orthogonal. And they all intersect at one point. Okay?
It's very bonkers.
It is. It's going to look like a lot of writing, but it breaks down into basically 5 things. 1, draw your parallels. 2, get a medial triangle. 3, draw perpendicular bisectors. 4, alternate interior angles theorem, right? Get those angles. 5, they're concurrent. Draw the bigger triangle. Parallels, right? Get a medial triangle. Get a lot of congruency symbols. Draw perpendicular bisectors. Alternate interior, get your angles, right? And you win. It's going to be a lot of writing. It's going to be alphabet soup. Because whenever we create lines, we got to label them, right? But you're going to be okay. Let's do it for real this time. Page 13. I made my triangle thick with 3 C's. It's the same triangle that you have, though. So first thing we got to do is we got to create the bigger triangle, right? What kind of lines do I need to draw to create the bigger triangle? What kind of lines do I need? What's your question?
Mine says C for H and egg.
Are you looking at page 13?
Yeah. Messed up.
Oh, oops. I had to recreate this. So if your letters are different than mine, change them. I had to recreate it because my computer wouldn't save. I had to recreate it this morning, but now I fixed the saving problem. I'm sorry? Of course. So first we got to create parallels, right? So I'm going to make a line parallel to BC. All right? So this guy's going to be parallel. Cool. All right. I'm going to create another parallel to AB. So this is about parallel. I'm going to do it as close as possible so we actually get a real solution. We're creating the Triforce. And then, can I have something other than red? What color do you want to use?
Purple.
Purple! Good choice. Good choice. Ooh, nice. That's going to be parallel. Rad. Rad. I know, right? Good color choice. Best color choice today, guys. Well done. First hour and third hour sucked at color choice. We had like orange, green, and like black at one point. Or like orange, green, and like red. Yeah. Alright, so here we go. So these are parallel. I'm going to do little parallel symbols, but you don't have to do them. I'm just being clear that they are parallel. Cool. So, how do I write that? Well, I write this. Let there be parallel lines. Let's call some dots here. I'm going to call this D, E, and F. So let's say let there be DAE parallel to BC. Right? That's what I created. That's the yellow lines, right? Be cool with that? I created the yellow. I'm also going to make FBE parallel to AC. That's the purple and the blue. DCF parallel to AB. Cool. That's it. Is it alphabet soup? Oh, sure. Right. But you call the points what you want. Right. I'll zoom in. I'll try to write most of it here and here so you can see it all at once. Okay. It's going to look like a lot because I'm using weird parts of the page, but it's not. So I created my parallels. Now, doesn't that mean that that's a medial triangle? right? So I'm going to say by medial triangle theorem converse. Okay. That gets me a bunch of congruent sides, right? You guys remember which sides are congruent? AC is going to be congruent to what two other segments? Let me write that as a B so you can see it, and an A so you can see it, and a C so you can see it. F, B, and B, right? So I'm going to write that. AC is congruent to BF is congruent to BE. Cool. Right, we know that has to be true. We also know that these sides go together, right? So I'm going to write those next. I'm going to do that in black because writing in yellow would be bad. All right, so I'm going to say that BC is congruent to AD is congruent to AE. Right? And then lastly, the blues. That's AB. And that's CD. And that's CF. Again, alphabet soup, but the thinking is not hard, right? If you're seeing the big picture. So we get all that crap. Now, we need that crap because doesn't that now mean C, B, and A are midpoints of the big triangle? Right. Those are midpoints. It's by definition. We're going to skip over it, okay? I'm going to give everybody a chance to catch up. We ready? All right. So medial triangle theorem is just the thing that says, hey, that's a medial triangle. So we get all those congruent sides. Right? Next step, what I'm going to do is I'm going to draw a line from here and make that a perpendicular bisector, right? This is where we're going to have to add a lot of letters, so just brace yourself. Okay. So I'm going to show you what I'm going to do for one of them. If I were doing this for real, I'd do them all at once. Okay? So I'm going to draw a perpendicular bisector here. I want it to be actually perpendicular. I don't have enough room. All right, that's perpendicular bisector-ish, I think, right here. Yeah. All right, so I'm creating a line. Now, that means that this is 90, right? Because I said I'm going to let it be 90. Okay. Which we then know by alternate interior angles. This must be 90. With me there? Cool. Yeah? Yes, you may. Cool. Now, I'm going to make all my lines so it makes it easier to do the letters. Okay? But that's what I did. Which means I get this by alternate interior angles, okay? We cool with that? All right. McKenna, are you okay with what I'm doing? Right, these two are parallel, so alternate interior. Right. I'm going to do the same thing for all these, and then I'm going to put my letters down. Because I don't want to have to duplicate letters if I don't have to. So I'm going to draw a perpendicular to here. So that's 90. And then I'm going to draw, oh, and that means this is 90 by alternate interior, right? Because we have two parallels, transversal cutting them, alternate interior angles. I'm going to do it for, I did it for B, I did it for C, I need to do it for A. And if I did it right, they should all intersect at the same point. Oh, good. That's actually a 90 degree. Yeah. This one's going on the wall, definitely. Right? Which means this is a 90 by alternate interior angles, right? Two parallels, one transversal, opposite sides. Okay. Now, let's label these things. I'm going to call the intersection point K, because I always do. Cool. So that's CK, and I need the other point where it intersects on the other side. So I've already used DEF. Let's call this G. Okay. For this one, I've got A, K. Next letter is H. Now, I'm not going to use H because H is sideways I. So depending on how I rotate the diagram, gross, right? Let's not. Let's go to J. Yep. And then B, K, I already used K, so I'm going to go to the next one, L. Losers. Cool. So what do I write to create all that? Well, I created CKG, and I said let it be the perpendicular bisector of what? What side is CKG the perpendicular bisector of? The blue side, right? Right? That's its perpendicular bisector. So what are we going to call this side? Yep. All right, I did CKG. Let's do AKJ. So AKJ, perpendicular bisector. What side is AKJ the perpendicular bisector of? Try it again. Yellow, very good, right? It leaves the yellow side at 90 and bisects it, right? So DAE. And the last one is BKL. So BKL is the perpendicular bisector of the purple side. So I'm going to call it EBF. EBF, yep. Whoever made the beginning of the alphabet rhyme. What's the Whiskey Tango Foxtrot for E? What do you say? What's E? Echo? Echo, right? Echo, Bravo, and then F is Foxtrot, right? Echo, Bravo, Foxtrot, right?
Military alphabet.
Right?
Oh.
All right, so now notice the perpendicular bisectors all intersect at K. We know that. We proved that last time, right? Perpendicular bisectors always intersect at one point. But check it out. This is from vertex to 90, right? And this is from vertex to 90. And this is from vertex to 90. So what are BKL, CKJ, and AKJ? They're all what? Orthogonals. So by definition, they're orthogonals. We're just going to skip over that, okay? So notice they all have K in it, so they all intersect at K. So now that we've got this, we're going to say, oh, we forgot about alternate interior angles, right? I did it on the diagram without doing it here. So I'm going to write that down. By alternate interior angles theorem. Can you guys still see that, sort of? Okay. I got that this angle, that's angle KCB, or KCF. Almost had KFC, guys. Almost.
It's not fried chicken. It's really good.
So KCF goes with this angle here. That's AGK. And so on and so forth, right? I'm going to do the rest of these. KCF, we did KBE. KBE, this angle went with this one by alternate interior. So that's KLC, or CLK. As in cluck. And then this one. That's angle EAK, or KAE. That one goes with angle, this angle, CJK. Okay. So colored in right angle went with non-colored in, colored in, non-colored in, colored in, non-colored in. Right. That's how we got them, by alternate interiors. I would highly encourage you to color in and not color in. Keep them straight, okay? So now we say, therefore, the orthogonals of triangle ABC are concurrent. Right, we left out the by definition, these are orthogonals, right? But I figured at this point, that's enough writing. Oh, sorry. Danny mode. Mark but small. That would be fun.
It's a reverse mark.
Like portable mark. This is true. Our Lord and Savior, yes. Yes, you may, just not in here.
Back with
Yeah.
I had it happen when I used to teach kindergarten. That's why I'm specific now. All right, so
What? Actually, you know what? That
he just pulled
happened
down his
to
pants, and I'm like,
me.
no! And honestly, it's my fault, right? Honestly, that's on me.
What did you say?
First time, that's on me. Second time, it's on you, kid.
Actually,
And I said I should have been more specific. I said I should have been more specific.
Mac, that actually happened to my mom's daycare. She said, yeah, I used the bathroom. Now we have to say use the bathroom on the toilet because
That's
they
right.
used to use the trash bin.
Yep.
And I had to clean it out.
You need to be specific with these kids. They need instruction.
They aren't the smartest.
My mom's
First day of kindergarten, it's like, everybody sit in a circle, let's get together. And then I realized very quickly after they didn't sit in a circle for like 10 minutes that these guys weren't just being rude. They didn't know what a circle was yet.
What?
So I had to teach them. Yeah, they had no preschool, right?
My mom has to be a preschool and now she's a kindergarten.
All right, so
Oh, I hate kids.
what did we do? A lot of alphabet soup, but really only 4 different things. Draw your parallels. Therefore, you have a medial triangle, so you get congruent sides, right? After you do that, draw your perpendiculars. You get congruent angles by alternate interior. And then you win. Don't memorize the alphabet, because you make your own letters, right? You can do the alphabet soup. It'll be a pain in the ass, but you can do it, right? Draw your parallels to create the big triangle. You get a medial triangle, so things are congruent. Draw your perpendicular bisectors, and then you get alternate interior angles, right? Then you win. So what is this saying? This is saying that the perpendicular bisectors, right? What center do they form when the perpendicular bisectors intersect? What center do they form? Perpendicular bisectors.
Ortho center?
Nope. Orthogonal kid orthocenter. Perpendicular bisector. Circumcenter. So the circumcenter of the big triangle, right? The center of the circle that goes around this guy, is the orthocenter of the small triangle, right? Because those are all orthogonals.
Welcome back.
There you go. Let's put this away. If we have time at the end, we'll come back to it. We'll give you another look, but I want to give you a break, okay?
Wait, is this a part of this, right?
Yeah, not really. I wanted to give it separate, so it's a separate grade.
Should I say plus?
No. Do not staple this in your packet. I want it to be a separate homework grade. Because some people are like, we need more homework grades. Which y'all are dummies, because you did all your homework, you got 100% out of that 10% of your grade, right? If I had more homework assignments, you still get 100% out of 10% of that grade, right? So it really just gives you more chance to fail. But you know, if that's what the people want. All right, so
And the people wanted a president.
here we go. Find the value of each variable. Guys, if you haven't already, go to number 3 and cross out x. When I originally made the problem, there's a way to solve for it. Yes. Yes, just not in here. You do not have to ask. That's why that's there. You can sign out instead of asking. And if you don't care to sign out, then why are you even asking? Right? So that's the thing you should do. If you really want to be that kid that asks, sign out. Or don't. I don't care.
Why didn't it sign out?
I don't care. It's for your safety. Like, if something bad happens in the bathroom, there's vandalism, then they can say, look, she was in there for 1 minute. She didn't do it, right? I don't think she's strong enough to pull off all the doors in the bathroom and spray paint the ceiling in a matter of a minute, right? It is Marissa. That's what I'll tell them. It was Marissa. Okay. She didn't sign out. All right, so, yeah, I just figured I'd offer you guys that. Because, like, I don't care. But in theory, you could get in trouble if you don't have an alibi, right? So, let's find the values of these. First off, what kind of center is G? What center is G?
A circumcenter.
Why?
As the perpendicular.
I see perpendiculars, I don't see bisectors.
Oh, shit. No, it's just bisecting.
Bisecting what?
Angle bisectors.
So these are angle bisectors. And where the angle bisectors intersect is always called what center?
In center.
In center. And the in center is called the in center because
It's inside.
inside a
Circle.
circle. That's inside the triangle, right? An inscribed circle. So there's a circle in here. So what does that mean these perpendicular lines are? They're not orthogonals, right? Because they don't go from the vertex to 90, right? That'd be the height of the triangle. Those are not the heights of the triangle, guys. What are those perpendicular lines then? What must they be? What must these perpendicular lines be? They go from the center of the circle to the outside of the circle. So what are they? From the center of the circle to the outside of the circle. What are they? Mm-mm. That doesn't bisect any angle. This guy? These are angle bisectors, right? What are the blue guys? They go from the center of the circle to the outside, radii. And if they're radii, one of them's 5. So what's the other?
5.
5. So x is 5. If you know your crap, this is the easiest stuff in the world. If you don't know it, it's impossible.
That's it?
That's it.
Wait, so you can't just like could you just say x equals 5, or you have to like put all the?
Nope, you can say x equals 5 if you know
You
it.
don't even have to like. Put
Nope,
the-
I know. You're welcome.
And that is because radii are equal.
Yeah, right? But you know it's radii because you know that's the incenter. How? Because those are angle bisectors. And you know the incenter is the center of a circle. Right? You need to know your crap, and then it's super easy. Right? If you don't know your crap, come see me. All right. Last thing, we need to find out what y is. We need to figure out what y is. This length right here. And need I remind you that if that's 90, then this is also 90? Right? How would we figure that out?
Hey, Mac.
What?
I have a question. Are
What?
you able to do Pythagorean theorem because of the 12? and
Yes.
5?
Because that's a right angle, this is a right angle triangle. What's the hypotenuse? 5y or 12?
12. Why?
Y, because it's across from the 90.
Tell me
So
why.
5 squared plus 12 squared equals y squared. What's 5 squared?
25.
What's 12 squared?
120 something.
144. 144 plus 25.
A lot. 169.
164
Nice.
plus- yeah.
169.
Good job. I love how you did that. That was great. Plus 20 and then plus 5. That was brilliant. 169. Nice. What's the root of 169?
169.
Come on, you should have this one memorized because it's 169. It's 13. Now you know 13 squared. It's funny.
Wait.
So y is 13. We're only able to do that because that's a right triangle.
Wait, so 5 squares because
25. Yep. A squared plus b squared equals c squared.
why are we doing that?
Guys, y, this triangle's a right triangle. And so that's the hypotenuse. A squared plus b squared equals c squared.
Oh.
Yep. G is the circumcenter for number 2. Now, if G is the circumcenter, first of all, if the circumcenter is on the triangle, what kind of triangle must we be looking at?
A right triangle.
What?
Right
A
triangle.
right triangle. Very good. So this whole thing's a right
I'm
triangle.
on a roll. I'm on a fucking roll.
Now, if G's the circumcenter and we have perpendicular lines going to it, what lines make the circumcenter?
Uh,
Oh, I know. It's
The radius.
perpendicular bisector.
Yep, so not only are they perpendicular, but they must be bisectors, right? So if this is 3, no. If this is 3, what's x? 3.
trace.
If this is 4, what's y?
7.
8. Double, right? How are we going to figure out z?
Okay, adding 6 plus 8.
8 squared.
A squared plus b squared equals c squared. I'll take it. Try the rest on your own.
Can we do like some marker delegation?
These can be lifesavers on the quiz, or they can be another thing that you don't know.
Mac
Make
would
sure
be
it's a
here.
lifesaver for you.
My dumbass.
Oh wait, I don't have a blue one, do I? 80 is a super. Okay.
Mag.
Are you okay? This is a lot of work. Are you okay? Okay, okay is good for numbers. It gets you to the reason. If you're okay, you're gonna lose fast.
I get your way every day, so sorry.
Yes. Nelly, you also were absent, so guess what? Bad grade doesn't count. We have a week to retake it though. It's the end of the quarter. Okay? But you're
Holy
gonna be
shit,
okay.
dude. I was going today. Let's go.
Yep. The only good thing about having quizzes that are over 2 weeks is the odds of you being absent are a lot higher, right?
Yeah, dude, right now I'm trying a USB-C plug, so.
Oh.
What?
All right. This one needs to go up there eventually. It just can't go up there yet because it's stuff that we're doing
Right now.
like on the quiz. Oh, so
Damn.
just make sure you don't do anything that looks like that.
Damn.
Although I doubt any of them would
Does
see
this
that.
count?
No, that's good. That's a great one to put up there.
I'll turn it upside down.
This is kind of up there doing it, but it's from the last quiz, so it's fine.
Oh.
What's up, McCartney?
something.
Go, 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 go.
I'm gonna go get a drink for a glass.
Alrighty.
What's up, Mac?
Hey, hey, hey. How are we, people? How are we?
We're good. Tucker.
Yeah, and as I promised, I have worksheets for you.
Did he do it? Tucker.
Oh, I need to.
Do what? Do what?
Brian, do you have a wooden pencil on you?
Of course I do.